Now let us see what is spectral efficiency or bandwidth efficiency of all the M-array modulation schemes which we have discussed. We have discussed M-array PSK schemes, FSK schemes as well as COM schemes. So first we will see what is spectral efficiency, and then we compare spectral efficiency of various M-array modulation schemes. So if you just take any M-array modulation scheme, any M-array transmitter transmits M possible signals, and it carries, each of the signal carries how many information bits? Log 2 M number of information bits, and the time duration taken by each of this is log 2 M TB. Therefore data rate would become the rate at which we are transmitting data to the channel is number of information bits divided by time. So since we are transmitting log 2 a number of bits, and time it is taken is log 2 mtb seconds, therefore the data rate which we are transmitting to the channel is 1/2 bits per second. And now we want to see what is the bandwidth occupied by this signal. So if you remember that if it is MPSK signal, the rate of all the M-array schemes will be same, but the bandwidth required will be different by each M-array scheme. So first start with MPSK, and we have seen that bandwidth occupied by MPSK signal is 2 by log 2 mtb or 2 by ntb, and so therefore bandwidth efficiency becomes which is number of information bits transfers in per unit time and per unit bandwidth. So the information which you are transmitting to the channel in per unit time is called data rate, and if it further divided by bandwidth, then it is called bandwidth efficiency. So bandwidth efficiency for the PSK scheme would become data rate, which is 1/TB, divided by bandwidth, which is 2 by log 2 md. So if you change this sign, you have to just swap it, log 2 mtb cross 1/TB cross log 2 mtb by 2, and TB gets cancelled. So bandwidth efficiency of MPSK schemes is log 2 m bits per second per hertz. And what is the conclusion? We see as M increases, the bandwidth efficiency of MPSK scheme increases. Similarly, we can find out bandwidth efficiency of a M-QAM scheme. Again, the formula is same, data rate which we transmit to the channel in per unit time and per unit bandwidth. So per unit time is log 2m divided by log 2m into TB, and bandwidth occupied by a QAM signal is same as the bandwidth occupied by the MPSK. So of course bandwidth efficiency of QAM and bandwidth efficiency of the PSK would be same. Okay, so we have seen bandwidth efficiency of the PSK as well as COM scheme. Next we'll see bandwidth efficiency of M-array FSK scheme. So of course, as I told you, data rate for all the M-array schemes is same, log to a number of bits transmitted in NTB number of 9 TB seconds, so bits per second, and this is division per hertz, and this is the bandwidth of the MFSK scheme, which we have studied in our previous class, that bandwidth occupied by the M-array FSK signal is M delta F, where delta F is 1/2 NTB or 1/2 log 2 mTB. This we have seen. Therefore, if you just solve it, this division sign will becomes cross, and you just write it as 1/delta F and put delta F as 1/2 NTB and solve it. It is very straightforward that you will get 2 log 2 m by n, and so bandwidth efficiency of FSK scheme would be 2 log 2 m by m. And one important fact is, as m increases, the bandwidth efficiency of FSK scheme decreases, whereas for QAM and for PSK, as m increases, the bandwidth efficiency increases. So now we have talked about what is the data rate which we are transmitting through the channel in per unit time and per unit bandwidth, right? But what about the error performance? It might happen that we have two schemes which might have same spectral efficiency, but they might give different bit error rate. So for this, what we do, we plot a this type of curve where we fix our bit error rate performance. For example, in this case, we are fixing the bit error rate performance of our setup as 10 to the power minus 5. So what we are doing, we are fixing our bit error rate to 10 to the power minus 5, and we are saying, okay, what is the corresponding value of spectral efficiency and corresponding and the power required to achieve this much of bit error rate performance. So this plot we have done here, that in y-axis we are plotting spectral efficiency and we are fixing the bit rate performance to 10 to the power minus 5. It means 1 out of 10 to the power 5 bits will be in error. So we have to ensure that only bit error rate performance of 10 to the power minus 5 is achieved. And we have to see what is the corresponding power required, and power is we are plotting in x domain in terms of EB by N naught. EB is energy per bit and N naught is the power of the noise. So let's just focus on the red part only. This red part corresponds to PSK, right? So for 8 PSK, what would be the, or for 4 PSK, this is 0.4, this is, so we are transmitting 4 PSK signal and we require 10 to the power minus 5 bit error rate, and let us say that at 10 dB we are getting this much of error, right? There is a formula to evaluate bit error rate of QPSK that we are not discussing here. Just you have to accept it at when we transmit 10 dB of EB by N naught with 4 PSK, we will get 10 to the power minus 5 error. So you just write here that this is 10 dB, just put a mark at 10 dB. Now at this 10 dB you have y-axis, what is the spectral efficiency, because we are plotting spectral efficiency. So each point gives you in x domain EB by N naught, in y domain spectral efficiency, and you can think that there is one more imaginary y-axis where this point, all of these points having same bit error rate 10 to the power minus 5. So what is going to happen here? You have to evaluate that at m is equal to 4 PSK, what is the spectral efficiency, and the spectral efficiency formula, if you see, it is log 2m by 2, therefore 1 bit per second per hertz. So the unit is bits per second per hertz. Similarly, now if you increase the value of m, now we are transmitting 8 PSK. So if you remember, I told you that if we go to the higher order, the error performance decreases for a given power, right? So if we fix the power or fix EB by N naught, and if we increase m, our error performance decreases. But we want same error performance of 10 to the power minus 5, right? So what would I have to do? We have to increase the, if we increase m and we want same error performance, we have to increase the bit, increase the power, right? Because as we increase m, the performance get poor. So for getting the same performance, which is 10 to the power minus 5, we have to power. So see, as we increase m is equal to 8, we go to the right. So we are increasing the power by some amount that we are not, there will be some amount by which you have to increase the power. Therefore you will shift it to this point. And at m is equal to 8, you can evaluate eta. So 10 to the power minus 5, it is fixed. In order to get 10 to the power same minus 5, if we increase m from 4 to 8, you have to increase it from 10 dB to some 10 plus x dB, and spectral efficiency corresponding to 8 is, you can evaluate 3 by 2, right? 3 by 2. So 3 by 2, just make it as per the scale. So just 3 by 2. For 16, similarly, if you increase the modulation size again, in order to get same error performance, you have to further increase the power from previous value to some more value. So and the error and the spectral efficiency is, you just put it here, log to 16 by 2, which is 2. And again we further increase to 32. You have to further increase the power in order to get the same error performance and the corresponding spectral efficiency with 2.5. So this curve very clearly tells you that what happens if you increase the modulation size. For the same given error performance, you have to increase the power, and how much spectral efficiency you can get. Now we will focus on QAM scheme, and I told you that QAM gives better error performance as compared to PSK for a fixed power. So of course, if we want similar error performance that we can get from QAM at low level of power, right, as compared to the PSK scheme. So this point you can see clearly from here, that if you want 10 to the power minus 5 error performance and your order is same, you can get it at lower value of power as compared to PSK. So black is QAM, so you will get the same error performance at lower value of power. So this will be some shifted, and since QAM and PSK has same spectral efficiency, these values for the is same. One important point is, see, at m is equal to 4, both QAM and PSK coincides, because this happens because, as I told you, that 4 PSK QAM error performance is same as the 4 QAM, this is 4 QAM and this is 4 PSK. So 4 QAM is same as 4 PSK. You cannot do anything in order to change its amplitude. So 4 QAM is, you can remember that 4 QAM is same as 4 PSK. Therefore, its error performance is also same. So we are getting 10 to the power minus 5 error performance at 10 dB of power, and we are getting the spectral efficiency of 1. Now we are discussing through this green line this same phenomenon for FSK scheme. What is FSK? If you remember that spectral efficiency of FSK is 2 log 2m by m. It means as m increases, your spectral efficiency decreases. Therefore, we start from here. As m increases, I have just written the corresponding spectral efficiencies, and I told you as m decreases, we get less number of same error performance we can get with some less power. So that is happening, that as we decreasing the value of m, as m increases, spectral efficiency for FSK decreases, but we get same probability of error at low, because this is true for all m's, right? As we increase m, the performance get poor. So as we increase m, as we increase value of m, the same performance you can get at